Hello everyone, and welcome into yet another live stream. How are you all doing? How is all of your days going? I, as always, forgot the music, because I always do. There we go. Hi there. Hi there everyone, welcome. Hi Mint, hi Led, blah blah. I am awful at pronouncing that. Let's try it again. Red, blue. Hi the Red, hi the Happy. I'm sorry Red, I just... Ah. Hi. Oh boy. It feels weird, it always does when I upload a video I've been working on for a while and then... Like, I'm not stressed anymore. It feels weird. Yeah, today we'll be doing some research, because obviously we'll be doing some research, as always, but this time there's no time pressure, actually. I mean, I still will have to script 2 more videos, and then make animations for 2, and then edit 1, but I'll manage after this stream. This new video model is getting me mixed up. Hi, the Tefta! Oh, hi! Oh yeah, pressure indeed. I mean, it feels weird. It just feels bizarre. For the past 4 days, I've been just walking a lot with scrap, making things. Not only this video, by the way. There'll be more video. There is. Okay, I don't want to say there will be more videos coming with scrap because I don't want to put that sort of pressure on Harry. His name is Harry. I don't know if I should refer to Scrap or Harry. On Patreon channels, I always said Scrap because I don't know. I like nicknames. I like them. I really do. Like I call people thieves. I call Tefta. I like nicknames. I'm gonna keep saying Scrap. So I don't want to put any more pressure on Scrap to actually make these videos with me. So I will instead say there's a possibility that there'll be a lot more coming. Because right now we're entering the chemical phase of the channel. We're going through chemistry. Some actual real chemistry. Speaking of, glassware arrived today. Hold on, let me get one. Who's the 15,000 subscribers? What? I have to cover a whole high school syllabus in 1 month. What should I do? That's another question. But unfortunately, I don't think I'll be able to help you with this one since I am awful at memorizing stuff. I really am. Hi, Toby. Hi, Thunder. Are you going to do organic chemistry? Eventually, yeah. I mean, that's what these live streams are for. We're just in the initial phases of the stream. In like, I don't know, 10 more minutes or 7 more minutes, we'll actually get into the research. And then we're actually really close to be done with the basics, which means that this live stream we might finally get into organic chemistry. The basics, obviously, of organic chemistry. We won't go too far. It's a lot to cover. Really awful lot to cover. But we might at least be done with the basics of chemistry. Or at least not so basics anymore. I mean, I don't know, orbitals and the way they bond is... You can hear it in the background. I know, I'm fully aware. This is just me trying to unpack the thing. Because, I do have a lot of glassware. Well, not a lot, but like a lot for another chemist. But soon I'll be doing some even more things with this glassware, and so I had to order some new one. And so this, for example, is this. Oh yeah. Welcome to Make It ASMR live stream. It's a 1 liter thingamajig. You know that thing, right? The thingamajig. That's its scientific name. Chemist. You check online. You'll see that you have like a test tube. You have like a crystallizer, like a distiller, and no way, distiller isn't it? Maybe this. I don't know. I'm not a chemist. Speaking of magician, the new model reminds me of a magician. It's a lumberjack. It's lumberjack. Kuan requested lumberjack, so I lumberjack. All right, that's enough. That's enough fooling around. It's time to get into it. Now, this is the periodic table, which is the first chapter, which is not the one we're on. We are actually on the 7th, I think, or 8th, or 9th, maybe even, of the first chapter. We're really far. We're gonna make it a day. Oh, yes, we are! Resonance. Oh, yeah, that's the... I think we went over resonance. Right here we'll have the ozone example, right? Oh, no. Oh, that's the one! Oh, we actually went over this, too. Yes, so we're getting into drawing organic structures. Oh, wait, we've been over this, too. Hold on. You can see at the very bottom. Oh, and the hybridization! Yeah, we also went over hybridization. Well, some of it, not... all of it, never mind! Ethane, ethylene, and acetylene, wow. Make it how to make a new... what's the matter? I am so glad you asked. This is LiberTex. LiberTex is a phenomenal website, libertex.org. Welcome to the non-sponsored sponsorship. I'm sorry, why? Why is this not secure? What? LiberTex. Since when? I'm sorry, where am I connected from? I am connected from Liechtenstein. Let me just... hold on, give me a sec. Hi there everyone, welcome to Jedna live stream. I am the... will not be valid until... oh no, it won't be valid till tomorrow. Well, I am so glad you're warning me, Firefox. I am so glad you're warning me. There, LiberTex. Yeah. Imagine this whole bit was the sponsored segment. Imagine if they actually paid me for this bit. Not my fault they forgot about the certificate. But yeah, it's a great website. I would really recommend, no matter what you want to learn. Everything is there. The web design is... I've complained about it before, and I will again. But anything, biology, business, chemistry, engineering, medicine, global, geosciences, Spanish, humanities, K-12, mathematics, physics, workforce, Ukraine, statistics, social sciences, everything is right there. So yeah, it's fun. Okay, anyhow, that's enough goofing around. It's time to get into it with bonding in ethane. Yes, right? Thanks. No worries, this is... listen, I love making arts for LiberTex, so my pleasure. Alright, bonding in ethane, let's see. Oh wow, that's the last chapter of the first one. How long is it? It's... we're gonna get into acids and bases, finally! Always wondered why they exist. Okay. In the ethane molecule, bonding picture, according to valence orbital theory, is very similar to that of methane. Both carbons are sp3 hybridized. This is the one where the orbitals form like a sink. I know I'll leave it for the video. Meaning that for arrangement that you can do geometry. The carbon-carbon bond with a bond length of 1.54 Armstrong or 154 picometers, if I remember correctly, is formed by overlap of one sp3 orbital from each of the carbons, while 6 carbon-hydrogen bonds are formed from the overlaps between the remaining sp3 orbitals on the 2 carbons and 1 s orbital of the hydrogen atom. All of these are sigma bonds. Okay, so... to put into picture, basically, right here, we have sigma bonds between the hydrogen and carbon, makes sense, and this is the hybridized... oh, it's bond only along one. This makes sense. Okay, so carbon has 4 valence electrons. I remember because in the video, like the most recent video, there was a segment about oxygen and carbon dioxide. And I remember, well, it doesn't matter. The point is, it has 4 valence electrons. On 2 on the s2 orbital, or 2s orbital. Shama, what did you just say? Oh wow, that message really threw me off. The point is, Yes, so these are hybridized sp3, so it's the second shell, first subshell with 2 electrons, hybridized with second shell, second subshell with 2 electrons. They both hybridize into second shell, second subshell with 4, right? No, wait, into a hybridized one with 4. That's why these have 4 different thingamajigs. And then 3 of those thingamajigs bond with hydrogen, and then 1 bonds carbon together. Okay. Imagine if hose blown. There's another head to it. I don't see it, honestly. Maybe? No. You know what? No. Because they are formed from the end-on-end overlap of the orbitals, sigma bonds are free to rotate. This means that in the case of ethane molecule, the 2 methyl CH groups can be pictured as 2 wheels on a hub, each one able to rotate freely with respect to the other. So, okay. Yeah, makes sense. If you remember correctly, pi bonds can't rotate, but this is clearly a sigma bond because they overlap head-on, which means they can actually rotate. That's interesting. Okay. Wait, that's... You know what? Let me note that. I like that. So we have ethane, in which it looks like this. Once again, I'm just gonna take the graphic because this is my personal notes. So I shall. We have a hybridized sp3, in which we carbon 600 bonds are formed from overlaps between each 3 bonds with hydrogen are sigma, and between carbons is sigma, meaning the internet really ruined the word sigma. It really ruined the word sigma for me. I don't like it. Meaning they can freely rotate. So yeah, so basically this one can rotate, this one can rotate, you know. This is the kind of the joint. Bang video earlier. Thank you very much. I really appreciate it. It really took a long while to make. Yeah, we're entering into a chemical section of the channel. I'm a chemist, so it's great seeing you delve into this stuff. I really wanted to get into chemistry for a really long time. It's just that it was a lot, so I knew I should first deal with the other stuff. And now that we're finished with quantum mechanics, at least temporarily, I suppose, we can finally get into chemistry, which is nice. And from chemistry, fun fact, you know what? I'm gonna spill this right now, or might as well. From chemistry, you know, I have this series of videos, which is called For What It's Worth, where the first one is basic math for quantum mechanics, second is quantum mechanics for chemistry, third one is chemistry for electricity. But fun fact, it will diverge. From now on, we're going into electricity, and also, on a tangent, we'll be going into biochemistry, because these are 2 different things, which require 2 different ways of tackling them, in my personal opinion. That's why I'm gonna get separate videos, because getting together electrochemistry and biochemistry into a single video, maths, quantum chemistry, biochemistry, biology, precisely. Well, between chemistry and biochemistry, there will still be organic chemistry, I think, because I mentioned, I think it deserves a whole other video. Chemistry is a study of matter. I like the fact put in brackets Heisenberg. Ah, that guy. Okay. Yeah, I mean, chemistry is a study of matter, but I like to think of it as a study of change, personally. I say organic can come before biochemical lead into it. Yeah, I think that's how I'm going to do it. Because for organic chemistry, I'm just going to talk about bonds, honestly. This is just, the organic chemistry is going to be 40 minutes of me talking about bonds and orbitals. This 99 of biochemistry is organic. Yeah, for biochemistry, I'm just going to do a cell. That's what I'm going to do. I'm just going to go over a cell. And then from biochemistry, we'll go straight to, I don't know, biology. I mean, biology... I was thinking biology as tissues, but... Organic was fun for me until it just became memorizing mechanisms. Oh no, I haven't gotten that far. Oh no. Alright. Bonding in ethane. So that was... ethane. What's the difference between these two chapters? Ethane and ethene. Okay, I see. That was ethane. Now we're going into ethene. I am not great at spelling, which I'm certain that won't be a problem. Fun fact, crazy ass conformers arise due to rotations of CC sigma bonds and absence of any pi bond in ethane. I don't know what conformers are. Alkenes. Yeah, this is going to be a pain for me. Okay. Oh, I'm certain this won't cause any problems in the future. Why would it cause problems in the future? Ethene. Key component of using valence bond theory correctly is being able to use the Lewis dot diagram correctly. Ethene has a double bond between the carbons and a single bond between each hydrogen. So, wait. Each bond is represented by a pair of dots which represents electrons. Each carbon requires a full octet and each hydrogen requires a pair of electrons. The correct Lewis structure for ethene fudge is shown below. It is ethene, right? And the other one is ethane. I'm not mispronouncing. I have no idea. Hi there everyone, welcome to another Make It Spreading Misinformation livestream. And hi there Aurelians. For more information on how to use Lewis dot structure, refer to... I don't know if I will be allowed to see this. Page unfound. I want a VPN. They don't like VPNs. Is this organic chemistry? Not yet, but really close. Really close. Yeah, it's more bonding fundamentals. But we are one chapter away from actually getting into the basics of biochemistry. No, not biochemistry, organic chemistry. Because these two are different, of course they are. Organic chemistry is the more fun one. Biochemistry is the... Yeah, that's... yeah. I don't put it on screen for today, yeah. As soon as organic chemistry starts, I'm dipping. Why? Organic chemistry is cool. Organic chemistry is cool. It does look like organic chemistry. It's not yet. This is just bonding and how things rotate. Okay, the number of bonds between them. Each carbon atom is the general arrangement of the general arrangement AX3, where A is the central atom surrounded by 3 other atoms denoted by X. I mean, makes sense. Yeah, we can see it. Compounds from this other trigonal planar geometry, forming 120-degree bond angles, because every single one wants to be as far away as possible. In order, that's the VS EPR, if I remember correctly. In order for the unhybridized orbitals to successfully overlap, the CH2, so one of these, must be coplanar. Therefore, C2H2 is planar molecule, and each bond angle is about 120 degrees. Diagram below shows the bond lengths and hydrogen carbon atom bond angles of ethane. Okay, so this is also on a single plane. Alright. sp2 hybridization. Hybridization is a fun topic, because I still get it and don't get it at the same time. Tell me your favorite amino acid. Make it my love. I don't know all that many amino acids. Alright. So, wait, hold on. Why is it... I mean... Okay, so it's planar. The whole molecule is planar because each submolecule, let's call it... I should clarify. Submolecule... Not written anywhere. So each submolecule, so CH2, is coplanar. I mean, this one must be coplanar. In order for the unhybridized p orbitals to successfully overlap. P is the second orbital. Chemists, listen. I've heard most people regret doing biochem because biochemistry is not fun. But there is a difference between biochemistry and organic chemistry. It should maybe... Okay, let's make it clear, pun intended. There is a difference. Organic chemistry is basically chemistry of large molecules, kind of, basically. Like, if you have molecules which have a lot of atoms, that's organic chemistry. Biochemistry is the chemistry or related to biological things. And that is a pain. The CH2 must be coplanar. Hold on. In order for the unhybridized p orbitals to successfully overlap. Alright. So we have hybridized like this, except in this case we Jesus. So like this, except not really, because we have these two, which hold on, I can crack this. Okay, give me. Let me cook here. I can crack this. I can crack this code. It's easy. You have 3 sp2 orbitals and 1 p orbital. Okay, yes. So these you can. Okay, so these are hybridized. Wait, no. Wait, yes. Who am I? What am I doing? What's the meaning of life? I'm struggling. It has 4 valence electrons. And the 3 sp2 orbitals. Okay, yes, so it's basically like this, except 1 orbital isn't hybridized. That diagram showing sp3. I know, but I'm just trying to use it because I don't know if I have an sp2 diagram. So it's basically like this, except this one isn't hybridized. This one is not being this specific one, only, you know, generally, like you have 3 okay, so you have 3 hybridized, 1 unhybridized. And then, in order for the unhybridized p orbitals to successfully overlap, so unhybridized are in between them. Each carbon atom is the general arrangement AX3, where A is the central atom, surrounded by 3 other atoms, this is denoted by X. Compounds of this form adopt trigonal planar geometry. Oh! So this has to be on the same plane, this has to be on the same plane. But then we'll still be able to rotate, so something... I'm fine. In case anyone, I'm fine, okay? I'm alright. Oh, Sammy, thank you so much for asking how you're doing, because I am doing swell, fine, and I am make it insert stream title. No, it's fine, I can get through this. It's just chemistry. How hard could it possibly be? Said the guy who's never done chemistry. They can't rotate because the p orbitals on both carbons need to be lined up with each other for the pi bond. So it's hybridized from the carbon's perspective. Hybridized, non-hybridized, and the fact that these non-hybridized p orbitals are overlapping, the fact that they are not hybridized, causes them to form the pi bond, which can't rotate because it needs sigma bond to rotate, and it forms a pi bond. Flame, you have okay. Is this your first time joining in or the second? Because I'm certain I haven't seen you for much longer time. The reason why I'm asking is because for most of these chemistry live streams, I have been very publicly complaining about one thing. And that is that when I was researching medicine, I had Ali, who is my medicine expert. When I was researching physics, anything, quantum mechanics, electricity, whatever, I had Alex, who's my physics expert. First time. I think I might have dropped a random message at some point many months ago. Well then, Flame... So, I am so glad you are here, because I was really terrified of researching this without having someone who understands it out there watching. Obviously, I don't want to pressure you into watching the live stream, because that would be a pretty awful thing to do of me. So I'm just really thankful you're here right now. Okay, so I get it. So we have hybridized, hybridized, non-hybridized cause pi bond, and pi bond means pi bond means no rotation. Okay. Oh wow, okay, that's simple in respect. You know what, in respect it's simple. According to Feinstein's bond theory, two atoms form a covalent bond through overlap and have each unpaired atom. In ethane, each hydrogen atom has one unpaired electron and each carbon is sp2 hybridized with one electron each sp2 orbital. The fourth electron is on the p orbital that will form the pi bond. Yes, so pi bond can't rotate. Okay, simple, I get it. Free to hop on Discord and explain things anytime too. Yeah, I only research on streams because my ego demands constant feedback. It's actually, what was it called? Oh, being vain. That's right. So, being an acetylene. Speaking of, I just realized that it's been how long? 27. It's actually been going on for 27 minutes. Really become a lot. Ethene, yes. I count going through ethane and ethene a lot, okay? This is difficult stuff. I'm barely a mathematician, not even a chemist. Okay, finally, the hybrid orbital concept applies well to triple bonded groups such as alkynes and nitriles. Consider, for example, the structure of ethine. I'm fine. Okay, so we have ethane, which is this. Can't rotate because is that you're understanding this stuff well. If you can visualize shapes in your head, then you'll be fine. Okay. Oh, that's really good. Alkene. Wait. Oh, but there is a convention to it, isn't it? Wait. Oh, there was a convention. Never mind. Oh, of course there's a convention make it. Oh, why have I never thought about that? This makes sense. Wait, what is the A, E, and Y based on? Is it based on the AX structure, or is it based on the bonds in between the central atoms? Or am I getting it all wrong? Because that is a third possibility, which I should make clear. Not that I'm bad, dislike science itself, I just don't have fun with it and it requires too much memorization. It actually surprisingly doesn't. A in a single bond? So it is based on bonds! Oh, I'm noting this down. That's set. Oh, yes, right here. This is gonna save me so much trouble in the future. Okay. A triple bond. Although I should know that an asterisk because bond in double bond wide single. I can't count. I'm not great with math, okay? Like you have like 1, then you have 2, then you have like 3. What's the time to memorize all these numbers? There's too many. Example, an organic molecule in the alkene category will have a double bond. Oh, I love it when things just click together like that. I think that's a set. You know what? I think that's a misconception we should clear up right this time of the live stream. When it comes to organic chemistry, this is the same thing which I found with medicine. So people are, for example, really afraid of getting into medicine because they think that there's a lot of memorization, that you have to do. And yes, that is true. There's a lot of things you have to memorize. But people who study medicine know this. And so they don't really want to make their lives harder than they have to be. And that's why you have these, I don't even know what to call it. I always describe medicine as the most well-behaved science because of it, where based on the name of something, you can already determine what is its purpose, what it is. Like, for example, itis. If some word ends with itis, then it's an inflammation, stuff like this. Meningitis is the inflammation of the meninges, which is like a thing on the brain, doesn't matter. The point is, I am so glad to see that it also happens in chemistry because this will make it, pun intended, so much easier. F is just part of ethylene. You know what the F for ethylene means? Carbon hydrogen? Right? In chemistry, when something has a really long name, you can work out the entire structure based on these rules. Oh, this is gonna be phenomenal. I know that there still will be plenty of memorization, because this is just a complex thing. We still will be. One only thing I remember from organic chemistry. Oh, I remember nothing, so... This is actually pretty nice, remembering absolutely nothing for the streams. It gives me a fresh start, you know? Okay, so meth means one carbon atom in the main chains. F means 2, prop means 3. Okay, I'm also noting... I should make... Hold on, I should set up a whole separate chapter just for... words. That's what I'm going to call it. Alright, then we have F, which is 2 carbon in the main chain. Then we have meth, which is 1 carbon in the main chain. Then we have prop, which is 3 carbons in the main chain. I don't like the etc. because that would suggest that there is a pattern, and I feel like I'm too dumb to see the pattern. This is organic chemistry fundamental from high school, but these names will come up in literally everything. I have a memory of a goldfish. I know nothing about chemistry. Well, I do actually now. Right now, I do know a fair bit. But when I started these streams, and before I actually contacted Scrap to make a video, back then I knew absolutely nothing. But 4.5. Okay, no, there isn't a pattern. It's completely random prefixes. I just said etc. as in... Oh, I see, okay. So I'm just gonna add ... And before hex... Wait, is it be pot and pent? Because, I mean, from pent and hex, there is a pattern there. There's a pattern after like 5. Yeah, precisely. There will be hex, so 6 carbons. Then will be hept. 7, I forgot. 7 will be hept. Probably. Not help. That's... I mean, help, you know, that's... I mean, yeah, but not quite for this, in this context. And then 8 would be nona, 8 would be octa, 9 would be nona, 10 would be deca, then would be undeca, duodeca, 3deca, quaddeca, quindeca, hexdeca, hepdeca, ocdeca, nondeca, vigin. One Vigin, two Vigin. So I'm gonna recommend googling for a clear table that shows examples molecules though. I will maybe, you know what, actually yeah, I should do it. No, Greek, what language is this? I think, I have no idea. I don't know, I just know these things. I don't know why, I don't know what even they are. Funky number name is precisely. So let's carbon main chain naming convention numbers thingamajig. There! Precisely what I was looking for. Oh wait, is that a list of all of them? There is no way. I should really get through this one of these. Oh, but organic chemical compounds recommended is published by nomenclature. Okay, so this is just all of the rules for naming everything. There it is. Dodeca, trideca, yeah. But it's 4. So let me just switch it up. I'll have to get through this one of these streams, because that's just really useful to know. Where's the music make it? Oh yeah, music is made by music. Funny you should ask. It's link in the description. https://youtube.com/add SodaCaseyMusic for all of this amazing music playing in the background. Would recommend go subscribe to Soda too. By the way, did you study it about alcohols? Mate, I'm barely on bonds. I'm barely going through bonds. Listen, if a molecule so far has 4 atoms, it's already a lot. I haven't even gotten into organic chemistry. Give me a second. Okay, this. So can't rotate because pi bond between 2 carbons, because unhybridized p orbitals. I have a finals for chemistry next month. Well then, Blendy. Hi, by the way, Blendy. Welcome to live stream. Well then, that's what timing? Aromatic compounds are pretty important. What's it called? Benzene? Yeah, it's benzene. To be honest, you're approaching chemistry from a quantum direction, which is completely different to everyone else. So all these sources are assuming knowledge you don't have yet. I suppose. Yeah. Listen, if I was approaching it from the right direction, it wouldn't be a make it stream. So, to be fair, almost everything I've researched so far, I've approached from a quantum mechanical direction, which... well, the word dumb comes to mind, honestly. Oh no more, we studied about those in school in a weird way, like, wrote everything, all names and some interactions between them, but with way less details. That's what I like. With this one, we have details. I think it's a really cool way to learn. I mean, the reason why I'm doing this is because, you know, Forward's Wolf series, in which I'm a huge fan of the concept of abstraction. As I've mentioned almost every stream, I'm a huge fan of the concept of abstraction, where you have things which have no abstraction, like quantum mechanics, the most basic kind of quantum mechanics, and then you add abstraction, which means you simplify and lose accuracy. So then from quantum mechanics, you get chemistry, from chemistry, organic, biochemistry. And so I like studying from the bottom up, just because then everything makes sense. It takes a lot of time, it's really slow, and well, I'm not really getting anywhere most of the time, but it makes sense. Finally, the hybrid structure orbitals concept applies well to triple bond groups such as alkynes and nitrogen. Consider, for example, the structure of ethene, common name for acetylene. The simplest alkene. This molecule is linear, or for atoms line a straight line. The carbon-carbon triple bond is only 1.2 angstroms long, or if I'm not mistaken, 120 picometers. In the hybrid orbital picture of acetylene, both carbons are sp hybridized. In an sp hybridized carbon, the 2s orbital combines with the 2px orbital to form the two sp hybrid orbitals that are oriented at an angle of 180 degrees with respect to each other. Along the x-axis, the 2py and 2pz remain unhybridized and are oriented perpendicularly along the y and z axis respectively. So like this. Okay, so there is a pattern which we already should note, and I'm pretty certain it's a pattern. I'm pretty certain it's not like a random thing, which is that right here we have sp hybridized, right here we have sp2 hybridized, and right here we have sp3 hybridized. Seems important. It seems important because right here we have pi overlap, and you know what pi overlap means? It can't rotate. I know how important rotation is. But I do feel like I should know how rotation is. Now we only see hydrologic carbons, then oxygen will get in, and will be about alcohol. There are also radicals. Have we reached those yet? No, I haven't. I'm on your bonds. Oh, maybe I have. Wait, hold on. Radicals. Let me enter my mind palace. Well, it's more like a mind shed or a mind porta potty. Radicals. I remember radicals. And radicals with extra electrons? Right? Let's see. 3 radicals. Molecules with odd numbers of electrons. Ah, it was odd number of electrons, not extra. Damn it! They are really reactive because they really want that extra electron. Okay. Each carbon atom was half filled. Okay, so this is all simple. Yes, sp3, sp3, sp2, sp3, sp3. The hybrid orbital concept nicely explains another experimental observation. Single bonds adjacent to double and triple bonds are progressively shorter and stronger than normal, such as the one in a simple alkane. The carbon-carbon bond in ethane, structure A below, results in the overlap of 2 sp orbitals. Okay, so this is 2 sp3 orbitals, as we've seen. This one, this ethane. In alkene B, however, the carbon-carbon single bond is the result of an overlap between an sp2 orbital and an sp3 orbital. Yes, because the CH3 is this one. Oh, it clicked. It's very new to chemistry. That is... Yup, I am. Very new is another statement too. When the chemistry clicks, it really... Oh, it really does feel like when the chemistry clicks. Wait, does that mean that right now we can basically take a chain, any chain, of carbon and hydrogen atoms, and we can determine the bonding between them? Because... Oh... Wait, this makes so much sense. Okay, this one makes less sense actually. Now that I look at it, this one makes way less sense. Whereas this one makes some little sense. Or maybe no, wait, it does make sense. No, it doesn't. No, it does. No, it doesn't. No, it does. Yes, it does. Yes, it does. No, it does. No, it does. No, it doesn't. It does, yes. It makes sense. Okay, so you basically take and check how many atoms carbon is... What's confusing about B? Nothing. I'm just dumb. I'm just really dumb. Okay, so we take carbon. Before we get in further, I like to ask myself, you know, I like to put out statements out there because what's it called? Survivorship bias, I think. When you read something, then you... I don't think it's survivorship bias. It's one of the biases. The point is, so does that mean that you take carbon, you check how many atoms it is bonded to, -1, and this gives you the sp(n) hybridized orbital. So for example, right here, this carbon is bonded to 4, which means sp(n) would be equal to sp4 -1, which would be sp3. Right here, this one's bonded to 3, which means this would be sp(n), which is sp3 -1, which is sp2, and this one's bonded to 4, which means sp(n), that's sp4 -1, which is sp3. Yes, that's a way to work out n is sp. I just made up the n, but It clicked! Oh, it makes so much sense. Oh, chemistry is amazing. Chemistry is awesome. Okay, all single bonds, but the bond in molecule C is shorter and stronger than the one in B, which is then shorter and stronger than the one A. Okay, so short bonds next to SPN isn't actually terminology. I'm just matching yours. Okay. Oh, yes. Wait, do you know where the N comes from? Number? I don't know. That's where I'm using it from math. You know, number as in the equation, like. As in, like, you know, SPN is equal to SP of X, where the X amount of bonds -1. That's. You know what the 3 actually means. Yeah, it's the orbitals. No? Yeah, isn't no orbitals? Hold it together, like. It's not from this. Where SP2 would mean less, like SP2 would be these 3. Then how many p orbitals there are hybridized? So SP, that's SP1 because 1 p orbital is hybridized. SP2, yes, okay. Oh, you actually, that spooked me for a second. I want to double check. No, it's fine, it's fine. It just really spooked me for a second. I honestly thought, oh, it feels like an ice sculpture, you know? Like, all you need is one crack, and the whole thing just falls apart. My entire understanding of chemistry just shattered. Oh. Alrighty then. That's it. And basis. We're finally getting into organic chemistry. The very, very, very basics. So far this was just the basics of chemistry, and now basics organic. In theory, when we see sp3, a correct way of writing should be s1p3. Okay, yeah, alright. Didn't make sense. Okay, the notation makes sense. But but you can skip the one in S just like you skip one in S1p1, right? Okay. Oh, Alright, so hybridization now doesn't make sense, and does make sense, which is the perfect state to move on. Skip the one. Okay. It's really like a cold shower when you realize that this is how I research for all of my videos. So for example, you know, for quantum mechanics, for example, I've been over the same exact thing. This just, and what's really funny is that for most of them, I researched this on stream, which means that for the most recent quantum mechanics video, for example, you can go back and actually watch the live streams where I've learned about the things which are in the video, and that kind of also takes away the illusion that I know it, because I don't know a lot. I'm not that smart. All right, I'm not that smart actually. Hybridization won't be mentioned again until it's extremely important that you understand the 100%. Oh, well, that's not great at all. I have to try and sleep at least 6 hours, but I'm glad I joined the stream. But live text. Bye, Fox. Good night and have a good night's rest. She was the strongest card of acid bases. Alright, acids, bases. I can do it. It's easy. It's just chemistry. How hard could that be? You're smart in the sense that you learn this stuff fast and explain it really well to other people after learning it. I'm just vain, as I mentioned. I need this constant. That's what powers me, you know. This constant social feedback. My ego demands it, and so I can feed it. So yeah, it's a really strong way to actually learn it. If you actually need this, what, social gratification, I think it's called. Okay. I need a second. Because this is... I can't do this sober. Alright. JN, not even gonna attempt to pronounce that, and T.N. Lowry independently developed the theory of protons, donors, and proton acceptors in acids-base reactions, coincidentally in the same region and during the same year. What a coincidence. Wild. The Arrhenius theory, where acids and bases are defined by whatever the molecule contains hydrogen and hydroxide ion, is too limiting. The main of Feigenbrau's lower definition is to identify the proton H+, transfer occurring in the acid-base reaction. This is the best illustrated by the following equation. Less known down, very important. Not basic, only basis. Although that would be pretty... Acids... Wait. Acid... Basics. There we go. Consider the pun finished. Equation. So, we have HA plus Z... Latex chemistry reaction notation. There'll be some good revision for me because my organic fundamentals are trash. Well, if mine are worse. The basis of chemistry, yeah. I know I'm funny. I'm really funny. Not what I'm looking for, although this would be. Oh, this is Chemfig. Wait, that's a package, not Arrow's chemical equations. Yes, I mostly mean the ones going back and forth. Latex chemistry, or latex arrows, maybe. It's very important for me to match the exact arrow, because if I just go with an arrow that goes left and right, then it's gonna be a different thing. It's always gonna end up being a different thing. Well, like this looks similar, for example, but what if like these arrows? No, these arrows missing the heads on the middle. It said it means something. I'm not throwing away my shot. Cool reference. Okay. Latex. Because no, this is harpoon arrow. Come on, there's no way there. Right, left harpoons. I knew it. I knew it exists. Right, left harpoons. Never mind, I take it back. Well, I guess we can just use the character. I prefer LaTeX because I can type it in, but there. Fine. The missing item is important, doesn't mean anything different in chemistry, don't worry. Oh, well then... Shucks. Then I suppose right, left arrows. Right, left arrows. Oh, never mind. No, never mind. Maybe Google doesn't have all the LaTeX. That, you know, I'm fine. Yeah, let's move on. Okay. HA plus Z is equal to A minus plus HZ. In which case, this is iron, right? Boy, acids and bases work together in this fashion are called conjugate pair made up of conjugate acid, conjugate base. Okay. A stands for acidic compound. A is the acidic compound. Then Z is the basic compound. In chemistry, it's important to use for that specific thing. Too many arrows. I can't even remember all of the letters. You have like A, B, C, A, B, I, K, G, B. There's too many of them. Who has the time to memorize all of that? Alright. A stands for acidic compounds and Z stands for basic compound. Why isn't this A, B? I don't know. Chemists hate me. I don't know. Alright. Why isn't this B? Why isn't this B? I'm upset now. Why isn't this B? I know there's a reason. Like, I know first, last letter of the alphabet, or maybe Z stands for some sort of zealous reactions. I have no. I'm saying there's a reason. Literally no idea what the Z is there for. Well, then never mind. Maybe there isn't a reason. Why isn't that B? It'd be so much. I always see base written right because it would make so much more sense, and also be A, B. Yeah, make it. Still. The thing you're researching. There you go. Right, yeah. So then we have A stands for acidic compound and Z stands for basic compound. Then we have as a list. A donates H to form HZ plus. Hold on. End equation. Remember the ABC rule. A bone coming through the bone is... Wow, what a cool way to memorize that. I always forgot about this. You know, I just come back home, there's like a bone going through my bone, I'm like, wait, is this normal? I never know. Z accepts H from A, which forms... This feels like a first grade math problem, you know? Ali donated 2 apples to form an apple pie. Zachary accepted the 2 apples from Ali, which helped him make the apple pie. A minus. Yeah, the A notations. Oh, damn it. This is already setting me up, but these are different. Doesn't matter. Becomes conjugate. Okay, never mind. The third sentence is not very first grade. Becomes. Alright. Becomes conjugate base of HA, and in the reverse reaction, it accepts H from HZ to recreate HA in order to remain in equilibrium. Right, obviously. I mean, yeah, no one questioned that. Obviously, A minus, hold on. Acid donates protons and accepts electrons. Base accepts protons and donates electrons. What about the third one? Not gonna lie, I understood these. A minus becomes conjugate base of HA, and in wait, conjugate. We've already been over this. So acid and base that work together in this fashion are called conjugate base. Okay, so conjugate becomes conjugate base of HA, and in the reverse reaction, it accepts H from HZ to recreate HA in order to remain in equilibrium. It sure does. And then HZ plus becomes a conjugate acid of Z, and in the reverse reaction it donates H2 A minus. Damn it, the perfection, recreating Z in order to remain equally cool. Conjugate base because the base you formed from the acid. Okay, so it's like a relative base. No? Right? Hold on. Conjugate base formed from the acid, which means A minus, which is the acid, becomes the conjugate base of HA. And in the reverse reaction, it accepts a H from HZ. Relative is a base by itself. So it conjugate as in becoming base. Yeah. A minus becomes conjugate base. Okay, so we have an acid and acid A, base B. So acid donates H. Wait, what is H? Is H just a random thing? Alright, H stands for a hilarious compound. So we have the acid, the H thing, and then the base. Very important that H is a proton. Okay, H is a proton. Makes sense, because H stands for proton. So we have we have an acid with a proton, and then we have a base. And then what happens is acid donates a proton to form basically a base with an extra proton. Now this one has a plus because it's positive charge, extra proton. Then the base accepts the proton from acid, which forms the base with a positive charge, extra proton. Then acid with a negative charge, because it just got rid of the proton and kept the same amount of electrons, becomes conjugate base of HA. Where did H come from? Where did this H come from? And in the reverse reaction, accepts H from HZ. Oh, so HZ gives it back to recreate HA in order to remain in equilibrium. HZ plus, because it's positive charge and additional proton, becomes a conjugate acid of Z, and the reverse reaction donates H. So wait, is it oscillating back and forth? Why is it going? I mean, this seems standard now, but this seems like just going back. How many apples on the apple? That's... You start with HA, an acid, to create the H plus and leave behind A minus, conjugate base of HA. Yeah, okay, makes sense, right? We start with HA acid to create H plus being obviously a proton, positive charged, so you end up with H minus, negative charge, because we just took a positive charge from it, so obviously it's not gonna have a double arrows that represent that the reaction is equilibrium and can go in reverse. Okay, so this is just the reaction going reverse, these two. Okay, so this is just going one way, and this really is just going back. Yeah, that's what it means. Inverse reaction moving left. Okay. Alright then everything is clear. Clear as it could be. Question, why is HA an acid? Am I supposed to answer that? Oh wait, hold on. Oh! Acid, okay. So, I mean, maybe we should. Acid's basics. So this, first of all, let me make this a bit smaller. That's pretty large. And then we have... So acids are basically compounds which have an extra proton, and bases are compounds which can accept an extra proton? Is that what it would be? How can A minus be a base when HA has was an acid? Because it got rid of the proton. And how can HZ plus be an acid when Z used to be a base? Because now it has a proton it can get rid of. It receives proton from HA. Okay, so that's this, yes. This kind of what I said, not really, but kind of close enough. We're gonna call it a close enough. Then H minus is a conjugate base because it is in need of H to remain in equilibrium and turn to HA. Okay, yeah. Alright. All of it surprisingly makes sense. Is that all acids and bases are? That's really... Calling it extra proton isn't quite right. It's more like the acid isn't holding the proton very well and the base will just pull a proton from it. Can. Okay. Okay, yeah. Sorry about that. Yeah, I really shouldn't have called extra proton. Makes sense. So just... More like a loose proton. So... Proton dies of an ace... Which, okay, let's try it again. Proton dies of an acid, but it's not really hanging on all the way. Loses a good word. Okay, then it all makes sense. It's all clear. It's all nice. All right. Basically, there are three definitions of acid and base: Arrhenius, Lewis, and Broston-Lowry. Oh, we're only going through over the first one yet. I haven't even gotten to the other two. Right, this is the... Wait, aren't the two of them though the same? Aren't these two the same? The Arrhenius I haven't... Oh, the Arrhenius is considered tool limiting. Okay, examples. Fantastic. Versus Lonely is one definition of acid base. Yeah, so because they both came up with it at the same time, which I think is comical. In the same year. Happy, are you doing well? Happy, are you good? Alright, acid examples. In aqueous solutions, acids and bases can be defined in terms of the transfer of a proton from an acid to a base. Thus, for the acidic species in aqueous solution, there exists a special derived from the acid by the loss of a proton. A species derived from the acid by the loss of a proton. These two species that differ by only a proton constitute the conjugate acid-base pair. Alright, so we have example. So convenient, so great. Parent acid, parent base. That's hydrochloric acid. Parent base, water. Right? That's right. Conjugate acid being H3O plus. So the addition of hydrogen is just okay. Oh, that is given from the. Okay, so the additional hydrogen, giving away additional hydrogen. So important thing to note here is that this is a plus, this is a minus, which means that whilst chlorine gives away the hydrogen, it keeps the electron, which means it effectively just gives away a proton. This hydrogen is just a proton, that's it, that's all it is. There's no neutrons in it, there is no electrons, it's just a proton. Okay. H plus is right now be like, though the atoms are molecules, I am alone the positive force. That's a really good one. Easy to imagine A minus can donate an electron, therefore it can conjugate base of the acid HA, where H plus have a tendency to accept electrons, therefore is a conjugate acid. Yeah, I'm just gonna stick with this one. Similarly, in the reaction of... Wait, hold on, music, stop. There we go. Similarly, in the reaction of acetic acid with water, Acetic acid donates a proton to water, which acts as the base. In reverse reaction, H3O plus is the acid that donates a proton to the acetate ion, which acts as a base. Once again, you have two conjugate. Oh wait, is that why? Is that why so many? Is that why acids have OH group? Because H is the proton you can discard, not discard, but you know, donate. And that's the word. Is that why OH is important for acids? I know, I suppose we'll get that. Reverse reaction H3O plus is the acid that donates a proton to the acetate ion, which acts as a base. Once again, we have two conjugate acid-base pairs. The parent acid and its conjugate base CH3CO2H by CH3CO2 minus, and the parent base and its conjugate acid H3O plus H2O. Not all acids have H, maybe. Which ones don't? This one? No way. Which one? Definition for now. Oh, the other definition ones. Okay, that makes sense. Yeah, but we don't care about the other definitions for now. Lewis definition of acid base. Yeah, but you know, that's a definition for another time. Let's stick to. How about we just stick to this one for now? Cause you know, how about we take it one definition at a time? Right, this all makes a lot of sense. They basically give away a hydrogen without the electron. Or in other words, a proton. Then parent base is the one where they have just electrons which can bind this hydrogen. Yeah, makes sense. Nitrogen of benzene. If we take sulfuric acid and nitric acid here, nitric acid behaves as a base. Yeah, but they still have hydrogen. Don't they? Doesn't nitric acid have hydrogen? Oh, sulfuric acid, actually. Correct me if I'm wrong, I think it has a hydrogen. Two of them. Bros Lewis definition of acidity. Oh goodness, we're going over another one. Why? We'll begin our discussion of acid-base chemistry with a couple of essential definitions. The first of these definitions was posed in 1923 by the Danish chemist Johannes. They're Danish, okay? We don't have to pronounce their name. And the English chemist Thomas Lowry, thank goodness. And has come to be known as the Bronson-Lowry definition of acid bases. An acid, by the Bronson-Lowry definition, is a species which is able to donate proton. Okay, so acid bases we have right here. Bronson-Lowry definition. BF3 fluorine. Oh. Is it using fluorine as a BF3? Oh, that's going to involve some pretty complex mechanisms, don't it? That's gonna involve some really complex stuff. If is it discarding just a single proton? You know what? No. Let's not get into it. We'll get there when we get there. First of all, Brown's law definition. Acid species which is able to donate a proton, base, proton, scepter. Gas from between hydrochloric acid and hydroxide ion. This one, okay. Not worrying about it until it talks about the other definitions of acid bases. Yeah. In this reaction, proton. Okay, so this is just the reactions, but all of them will be the same, right? Just yeah. So basically, give away a hydrogen right here, and come back. Once he makes its reaction, he sees how orthoboric acid works. Is that the BF3 one? Won't be fun. See several examples where a relatively reactive pair of electrons in a pi bond act in a basic fashion. Okay. I don't know what curved out diagram mean, by the way. It's just... no. Reaction protocol case. Hydroxide, as we learned in the previous chapter. Curved arrow depicts the movement. Curved arrow depicts the movement of electrons, the bond breaking. Okay, movement of electrons. Got it. Understood. Sick. Movement of electrons. Da. Nah, right. Oh, so the electron moves from the nitrogen to hydrogen, and then this electron rips it off. Electron movement or attack. Okay. Got it. I'm not doing the exercise. I refuse. I'd rather be confused. It makes for better content. What you're learning right now is the basis and literal opposite of oxygen reaction. It's the same logic of acids and bases, but with an electron instead of a proton. Yeah, but wait. If it's electron instead of a proton... Wait, what do you mean? Whoa, whoa, whoa. Hold on now. Isn't this just the acid and base reaction? Because you can see that, like, the hydrogen moves over to the base. Well, by hydrogen leaving the electron behind, so being basically just a proton. Understanding females is harder than this. Just unprompted with... unprompted. Unrelated to anything. Just throwing that out there. Got it. Hydrogen moves by the electron moving. Yeah. Okay, so it is just acid base. Sick. Neat. Now I understand it perfectly. Let's go on to get confused. All of these chapters are short, which I like. I like that. There are no doubt. You are no doubt aware that some acids are stronger than others. Yes, sulfuric acid is strong enough to be used as a drain cleaner, and it will rapidly dissolve clogs and hair and other organic material. Not surprisingly, concentrated sulfuric acid will also cause painful burns if it touches your skin, and permanent damage if it gets in your eyes. There's a good reason for safety goggles you wear in chemistry lab. Acetic acid vinegar will also burn your skin and eyes, but it's not really strong enough to make an effective drain cleaner. Water, which we know can act as a proton donor, is obviously not a very strong acid. Even hydroxide ion could theoretically act as an acid. It has, after all, a proton donate, but this is not a reaction that we would normally consider to be relevant in anything but the most extreme conditions. Bonds need to be formed and broken in order to move it from one molecule to the other, and that's why that's what the curly arrows represent. Alright. Relative acidity of different compounds or functional groups, in other words, the relative capacity to donate a proton to a common base under identical conditions, is quantified by a number called dissociation constant, abbreviated K of A. Okay, the common base chosen for comparison is water. So, acidity in relation to water. Well, common base being. Alright, so it feels like just electronegativity except acids. It's going to be the same, isn't it? Where like you can't recalculate the exact value, you can only no, it's fun. Alright, then we have next one, which is this constant. Better see as a form of electron donating, accepting. It's about how things hold on the proton. Alright. Oh yeah, so it really is like protononegativity. Or protonopositivity, I suppose. And you know what? I think we all should have some more protonopositivity these days. Okay, alright. And it is the relative capacity to donate a proton to a common base under identical conditions. So it really is... Alright, neat, sick. Amazing. Wonderful. How long have I been streaming for? An hour and 60 minutes. Okay. This is exhausting. This really is exhausting. Oh. Do I see here? Watch your video. Kuan, hi! Oh my goodness, sorry, my Kuan alarm just went off. It's the alarm that plays every single time you join in anywhere. Hi, the Kuan! Pay attention to the equilibrium arrow. They're showing that, showing in that reaction diagram above. You mean this arrow in the middle? Alarm from what? It's an alarm which plays whenever you join in. That long story. Okay. Dynamic equilibrium is reached with a proton transfer going both directions and finite conservation of pressure plate. The nature of this equilibrium situation, as we call it general chemistry, is expressed by an equilibrium constant. Yeah, I do. The equilibrium constant is actually a ratio of activities represented by a symbol A, but activities are rarely used in courses other than analytical practical chemistry. To simplify this discussion, for general chemistry and organic chemistry courses, the activities of all the solutes are replaced with molarities. The activity of solvent usually water is defined as having a value of 1. I am so tired. I am so tired. I can feel myself getting slower and slower. Should I leave it for the next stream? We went over 4 sub-chapters today, right? This is the 4th one, I think. I need an explanation for why they alarm when I join in. Should I be scared? No! The green flag. When's the next stream? And I think 8 hours if I'll make it happen. Hopefully. I'm just gonna go walk, spend the entire night walking on videos, and then tomorrow morning, 8 hours. Yeah, I don't sleep. Equilibrium constant depends on many things, like for example, tendency of the reaction to go back and forward, equilibrium. I may or may not make it. Oh, shut the line! Yeah, but don't worry, I do stream quite literally every day, so if you won't make it, pun intended, then you're not really missing out on much. Damn, that's what we're doing in chemistry class right now. Well, yeah, see, we're on topic. I wonder how far do we have to go, though, to get into the advanced stuff. Because I know, that's basics. I really am curious. Because this is a long textbook. Precisely why I chose it. It's fun. $15 is benzene. So when 15 will... Oh my goodness, wow! Destiny! Make it theme. D-theme 3 playing in the background. Make it streams every next day, not every day. What do you mean every next day? I beg to differ. The whole thing is streaming every day. That's the whole point. Anyhow, I'm gonna go now. I have to take a guess. We started this year in chemistry. I'll be from to 11th chapter. What's the 11th one? Let's see. Alkalines. No. Hold on, make a team is playing. You know what that means. I have to go now. So, that'll be it. Thank you everyone so much for helping me. Flame, I cannot thank you enough. You really carried me through this entire live stream. I'll try to have one in the future streams. Gonna help you like this stuff. It's kind of fun. Thank you so much, Flame. I really appreciate it a lot. And I hope to see you next time. For now, that'll be it. Thank you everyone so much for watching. And have a great day. Bye.